thank you to the organizing committee for the opportunity to speak at this conference. I'm Daniel Boice. I have my affiliation as Scientific Studies and Consulting. That's a small business that I started in San Antonio, Texas. And as such, there's only 2 employees, myself and my wife. My daughter and my son-in-law help occasionally out on this work. And I want to let you know I am open for business. So if you see any collaboration possibilities, let me know. In fact, my tax preparer requires me to say this so I can write this off as a business expense on my next tax forms. So my affiliation at the time of the submission of the abstracts was also with University of Sao Paulo, where I spent 1 year as a visiting professor with my longstanding colleague, Professor Amori Dalmida. Susan Holmes was a graduate student of mine who's now at Southwest Research Institute, also in the Republic of Texas. Here is my outline for the talk. And this is a follow-up on some updated work that we presented at the Origins Conference in Nara a few years back. Well, just as a brief reminder, of course, phosphorus is not well known, not very abundant in the universe. In fact, it's below a part per million in cosmic abundance. And what we can see, of course, is that there is a concentration in these elements that are necessary for life in the Earth's lithosphere. So the planetary surfaces have a very nice environment for availability of these biogenic elements. Animals and molecules necessary for life, like RNA, of course, have a great concentration in phosphorus. And I've compiled a list now of cometary volatiles, elemental abundances from some of our latest results of what we know about comets. I should have said I'm an astronomer and my background is science of comets. So you can see also there's quite a concentration of these biogenic elements too. Phosphorus we really don't know much about, particularly in the volatile phase of comets. There's just recently only a very recent detection of phosphorus from the Rosetta mission, as Harv mentioned in his talk on Monday. Putting this together, we can imagine, sometimes we have a hard time understanding large and small numbers, so I made a small analogy of the more than 7 billion people on Earth. If we could imagine the phosphorus people, there'd only be about 2,000 of them in the whole Earth's population. There'd be 25 in Vietnam, and unfortunately in NHON, probably none. Maybe one every year might pass through Queen. But if we look at the, as opposed to the cosmic abundances, the abundance of phosphorus in some of these molecules necessary for life, we might have, say, 3 in this room. So as you look at the person next to you, he or she may be a phosphorus person here. Of course, phosphorus is very important in many of the necessary conditions for life. As you know, metabolic molecules use phosphorus, cell structure using phosphorus, replication, and invertebrates, bone structure, depends on that element. So although phosphorus is relatively rare cosmically, even though it's concentrated in planetary surfaces, it is very essential for life. And when we do find phosphorus in the environment, we see that there are phosphates that have extremely long stability, but yet we do need molecules that can be very rapidly manipulated too. So we have this kind of a dilemma, or we have this phosphorus paradox where we where, of course, some molecules are bound so tightly to where it wouldn't be available for life to really use the phosphorus for biological functions. So, since phosphorus is important and present in these biomolecules, as I noted, and is actively scavenged or concentrated in environments, then the source of phosphorus on the Earth is also important for origin of life questions. So the question that I wanted to investigate or start down the road was, could extraterrestrial sources have been important in the delivery of phosphorus to the Earth? And so kind of laying some of the groundwork, since there's not a lot of observational evidence for phosphorus in the small bodies, particularly in comets, to look at some of the possible simple molecules that might be found in comets that could be delivered to the Earth. Inspired by a famous scientist, Louis Pasteur, chance favors the prepared mind. And then going on, how did this get in here? This, well, that was a first draft of this. I wanted to include an extremophile here, and I did. Breaking news was that the re-election campaign for Trump has a new slogan. I guess he's trying to appeal to our audience too here. Should I delete that slide? How many people vote I should delete? Okay, never mind. Okay, cometary delivery of phosphorus. Of course, people have looked into this issue for half a century or so. Bringing in the necessary prebiotic molecules kind of made the essence of life. Phosphorus-bearing molecules, could they actually be soluble in water? Of course, phosphorus molecules also have been identified in the interstellar medium ices, which may have been incorporated into cometary nuclei. Of course, there's also the issue of survivability by impacts. This has been also investigated, and there's not a clear definitive answer one way or another on some of these issues. But the question I wanted to look at is, if there was a delivery of phosphorus by comets, what would be some of the likely molecules, and what would be its relationship relative to meteorites and asteroids? Phosphorus observations in space, it's been identified, of course, in giant planet atmospheres, interstellar medium, circumstellar shells. Even in sunspots, we see some simple molecules of phosphorus. Meteorites studies, of course, have identified many phosphorus-bearing molecules too. And as far as comets go, the first tentative detection was in the dust component of Comet Halley. There was an impact analyzer for the dust, and the idea was the relative velocity would be so great that it would just vaporize, essentially reduce the molecules down to their atomic composition. So phosphorus was found, but the molecular form was not known. And stardust samples, a similar situation. The paper by Flynn et al. Has announced that there was elemental phosphorus found, but again, molecular form at least hasn't been published that I know of. Some observers have searched for phosphorus, going back to Hale-Bopp, some of the more recent comets, but only upper limits have been found in simple molecules like phosphine. And then the Rosetta results that were mentioned on Monday, there is a detection of phosphorus ion in mass spectrometer. but the parent of that is not well known. It's assumed that, well, it's consistent with phosphine being there, but the investigators are not prepared to say exactly what the parent molecule was. So we might expect some simple diatomics to exist and other simple molecules. In our study, we decided to start with phosphine in analogy to nitrogen chemistry, where we see a lot of ammonia, so very highly reduced form. And then what would be some of the implications of that hypothesis that phosphine was actually in the cometary ices? The idea is that as we observe spatial profiles in a comet, we can use a comet chemistry model, and by understanding the chemistry that occurs, we can work back to the abundances of volatiles in the ices that are in the nucleus. You can kind of undo all of the processing that's occurred in the coma, and then we can get implications for the organic inventory, look for prebiotic molecules, make speculations, and loop through our findings here to find out more about what these messengers from the beginning of the solar system are telling us. However, it's been pointed out, of course, the difficulty is understanding the data, the messengers that are coming from these messengers. Okay, to do so, we have put together a model now almost 40 years, working primarily with Walter Huebner and other collaborators to model the gas phase chemistry that occurs in the atmosphere of a comet. It's a multi-fluid hydrodynamic gas flow, which looks in quite some detail about the chemistry that can occur, photolytic chemistry, gas phase chemistry, and the like. This is the strength of going into detail of the various chemical reactions that we would expect there. So if we may start out with a dozen or so native molecules, and that can be transformed into hundreds of species through chemistry and the collisionally coupled inner coma here. And we also include things like optical depth effects within the coma. We include dust particles that can interact with the gas. And the result are one-dimensional spatial profiles. You can map out the velocity for the various fluids, the temperature profiles, and the like as a function of distance away from the comet and heliocentric distance. And here's a schematic of what I call the Scientific Studies Consulting Comet Code, also named Suisei, which is comet in Japanese. Chemistry model, the dust model, a fluorescence model, and a model for the evolution of the gas within the porous sublayers of the comet, putting that all together with the various processes that are connecting these lines, and then analyzing perhaps what the synthetic spectrum might be like. In fact, I suggest that you don't ever name your code virus. The management at your institute will probably heavily object to that, as mine did. But it's a perfect acronym, Virtual Universal Spectrometer. And in addition to the spatial profiles, one thing that we can do is we can look at the top 10 reactions, for instance, which are important for various species. This, for instance, is for HCN. And we can map those out as a function of cometocentric distance away from the nucleus. Here would be the nucleus, and then reaction rates, and we can look at the various importance of the production and destruction mechanisms for the various species. The red would be a destruction mechanism, black would be a production mechanism, and we can see that these, I've labeled a few of the chemical reactions. Here's just a photodissociation of HCN. Here's a proteinization of HCN and the like. You can see that there are relative importance changes as a function of distance from the nucleus, and we can also do a series of heliocentric distances, and we see that these reactions also change in importance as a function of heliocentric distance. So we can start to unravel what are the major bottlenecks, what are the major pathways to form these species. As we know, photochemistry is very important. When a comet comes to within about 3 AU of the sun, the solar UV initiates a whole lot of photochemistry, which leads to highly reactive radicals and ions, which interact via gas phase reactions in the collisionally dominated inner region. Photoreactions also produce very energetic electrons. So the electrons participate in the chemistry by electron impact reactions, electron recombination, and the like, which we've pointed out for many years should be important in comets. And starting with our hypothesis that phosphine would be the phosphorus-bearing component, we see that we can find some photodissociation. Reaction rates for phosphine here, we note that if we look at proton affinities, water being the dominant gas in a comet, molecules with greater proton affinities, of course, are going to undergo protonization reactions. And we find that protonization reactions are very important also to understand the chemistry of comets. Phosphine has a relatively high protonization, so we would expect these reactions to be important in the coma of comets. So we added a number of phosphorus-related reactions and species. Many, of course, are not very well known. And we first create these forest wheels, which is, in fact, in Texas, the way to say ferrous. So you're not incorrect if you actually pronounce it forest there. That's for pH. And here's kind of the bottom line of the chemical network. For phosphine, we see major destruction pathways in red, and major production pathways, arrows leading into a species in blue. The thickness of the arrow indicates the dominance of the reaction, thickest being the most dominant, thin being an order of magnitude down, and dotted meaning 2 orders of magnitude down. And what we found was very interesting was that this protonization reaction is very important. And so any collisions of phosphine with one of the hydrogen group species, water group species, leads in the transfer of a proton, and then quickly it recombines with an electron. It goes back to phosphine. But in the meantime, it leaves phosphine in a very excited rotationally vibrational state, which will quickly de-excite down to phosphine. So we call this a recycling reaction, where the original phosphine that comes from the nucleus can undergo this recycling reaction many times. That's going to extend the scale length within the coma, and also going to lead to the emission of hot bands, collisionally excited or rotationally, vibrationally excited molecular bands that are produced by this recombination reaction. And we see a lot of the species that I showed on the previous slide for proton affinity also would undergo these recycling reactions. So just in summary, we see that the model reproduces the relevant chemical reactions that we think would be important in a comet coma, and we've particularly identified protonization as an important reaction. We would expect other phosphorus-bearing molecules to be important. The scale lengths for phosphine are relatively short, photodissociates very quickly, but it can be extended by 3,000 kilometers or so for a typical type of comet due to this recycling. Electron impact reactions, we believe, are also important. We also note that it's a super volatile, so we would expect probably for it to be, for a sublimation to occur in the range of much more volatile ices like COCO2, could be seen at larger heliocentric distances. And then my last summary slide here is just a reminder of protonization of other species. Should also be very important. So people with mass spectrometers going through the coma of a comet should be looking for some of these other very important protonated species. Recycling, as I mentioned, extends the scale length, results in these hot bands. In the case of HCN, we also get isomer formation. A certain fraction of them going through the recycle loop actually go to HNC, which has been detected in comets. So it could be an important source of HCN through chemistry in the coma. Other likely species, well, we're going to try to extend the study to other very simple phosphorus containing compounds to get a handle on what we might expect to see. One thing for sure, we would need a very bright comet, very high production rate comet, and very near the Earth. Since the range is very limited, since the abundances would be very low, it would take maybe an unusual comet for ground-based observations. And I'm working with astronomers in Japan, led by Hideo Kawakita, to look for these types of simple phosphorus-bearing compounds in comets. So I'll more or less leave it there. Come on. Thank you. Very nice astronomically themed flag, a star. But as we know, stars should have comets around them too. So I made a slight suggestion for maybe the Vietnamese. Maybe there should be some exoplanets too, or habitable zones or something like that. So.
Thank you very much.